So here again is our series and its almost computed form. Here I changed the numbering slightly. So it's the sum of the alternating terms which I have denoted as j of n. So let's look closely at what is happening with terms one by one. The zero term is j naught is 1 over lambda. The next one is obtained by multiplication by the fraction 1 over lambda. So it's 1 over lambda squared. The next one, j2, is obtained from the previous one by multiplication by 2 over lambda fraction. j3 by multiplication by 3 over lambda fraction. So the factorial starts accumulating in the denominator. Finally, jn is obtained from jn minus 1 by multiplication by fraction n over lambda. Now look at this fraction closely. If n is greater than lambda, then jn is greater than jn minus 1. But this is a very serious thing. That means that for any finite lambda we take, there is always number n naught equal to lambda or its integer part, such that terms jn with indices higher than n naught starts to grow. So the terms of the series are unbounded. But that means that the sum diverges for any finite lambda. Before analyzing what to do with it, let's think how it happened. Well, we used Taylor expansion for 1 over 1 plus x function when computing the integral. This seemed reasonable since the integral is dominated by fast decaying exponential with large decrement lambda. So the important x domain is small, from 0 to 1 over lambda. But still, the upper limits of the integral is plus infinity. But the Taylor series is convergent for modulus x is smaller than 1. So the segment from 1 to plus infinity is forbidden for integration. Yet we integrated, because all our integrals were convergent, so why not? But this is precisely the reason why we got the divergent series in the end. Well, you saw the famous opinion by Niels Abel about the divergent series at the beginning of the lecture. And yet we saw that this series was not so bad. As you remember, if you sum up the correct number of terms, it gives a very small error. So this kind of series behavior is called an asymptotic behavior in mathematics. The series itself is called an asymptotic series. I'll give you later a formal definition. But right now, let's plot the error function, which is simply the modulus of the difference between exact integral and partial sums of our asymptotic series. We plot it as a function of the number of the corresponding approximation terms entering the partial sum of the series. And we see what we expected to see. It's not monotonous. So there is an optimal number of terms in our series, which give the minimal error possible. We already saw it on the video a couple of minutes ago. That it was also around n is equal to 5. And, by the way, the error is not so large. It's just 0.008. And the value of the function itself is around 0.2. So the accuracy is still around 4%. Isn't it incredible that the divergent series can give such an accuracy? And yet this accuracy is quite feasible as long as you know how to handle this series. At this intriguing point, we close our introductory remarks on asymptotic series and switch to the detailed discussion. So we stopped our discussion last time at the divergent series for the integral. It happened that the series, despite being divergent, yielded accurate results. If handled correctly, it was possible to achieve the accuracy of 4%. Now let's accentuate the difference between the divergent asymptotic series and convergent Taylor series. Consider another classical example, the exponential function e to minus lambda. It has a convergent at any lambda Taylor series expansion. Let's see how well the Taylor series approximates it. Let's take reasonably large lambda and build partial sums of the Taylor series. First, let's plot e to minus 10. So these are our axes. The horizontal line represents the number of terms in the Taylor partial sum. The vertical one is for the value of the partial sum itself. So e to minus 10. It's a really small number, of the order of 10 to minus 5. Here it is, the red line going close to the horizontal axis. We plot the value of the sum of 1 and the first non-trivial term in the expansion, which is minus 10. It is this red dot. Next comes the second non-trivial term, which is 10 to 2 divided by 2 factorial. Then the third one. And we see what's happening. The partial sum yields oscillating result. And oscillations get bigger and bigger when we add up senior power terms. We see that after 7 steps we reach 1000 as a value of partial sum. And it still grows. At the 10th step it reaches the value of approximately 1300, which is the maximum value before it starts converging toward the real value of the function. But it takes 20 terms to get the answer with reasonable accuracy. Let's analyze what we have just seen. First, the partial Taylor sums are extremely inconvenient as a way of representation of our function due to their oscillating nature. The actual value of the function is the result of the tiny mismatch in subtraction of big terms. The result is a tiny number, 10 to minus 5, yet it arises from the combination of terms of the order of 1000. Just look at these two orders. It's an 8 orders difference. It is due to the alternating sign that such cancellation is possible. Comparing the orders of the result and the order of intermediate terms, we conclude to get the normal accuracy for e to minus 10 from the Taylor series, we need, first, to keep a significant digit in the process of computation, second, at least 20 terms of the series. And this is just e to minus 10. Imagine what is going to happen for e to minus 20, for example. So Taylor series, despite being convergent at all, is completely unacceptable as a way of calculation. The fair question is, how do we compute e to minus lambda then? Well, the easiest way is to compute e to lambda instead. Its Taylor series has no sign flips. And the second step is to build the inverse function to obtain e to minus lambda. So this was just the example to show you that convergent series is not necessarily the most convenient one, as it can be practically useless. This issue started receiving attention through the whole 19th century. One of the mathematical physicists who became interested in the phenomena was George Stokes. In 1847, he wrote a now celebrated paper on the theory of airy functions. He was probably the first to explore the divergent asymptotic series and use them as a powerful approximation tool. And this is his quote. These series, like expansions of e to minus x, sin x, cosine x, are convergent for all values of the variable x, however great, and are easily calculated numerically when x is small, but are extremely inconvenient for calculation when x is large, give no indication of the law of progress of the function, and do not even make known what function becomes when x tends to plus infinity. His paper on what is now known as Stokes phenomenon became a classic of mathematical physics, and we devote the whole lecture to this topic in what is coming. But now back to our series. Here again is our integral and the asymptotic divergence series. In order to make some precise statements about the precision of the expansion, we need to contrive some estimate for the error of our approximations. As you remember, the way we obtained this series was not rigorous. In fact, it had a serious flaw as we used the Taylor expansion of function of 1 over x plus 1 beyond its region of applicability. But to make an accurate estimate, we need to develop the technique which is free of this flaw. Fortunately, this technique is quite elementary and works beautifully in many cases. It's a very familiar integration by parts technique. So here we go. First, we exploit the fact that the exponential has a simple antiderivative, and we turn it into the derivative. And then we perform the first integration. Working out the limits of the first expression, we obtain the following result. And this completes our first step. Let's repeat the same procedure again with the remaining integral. Again, we turn exponential into derivative and integrate by parts once more. Calculating the second term and performing differentiation under the sign of the integral, we arrive at the final expression. And this is our second step. For the clarity of pattern, you may do it the third time. Just notice that the remaining integral has the same form as the initial one, with the only difference is that it has additional cube in the denominator. This will yield the additional 3 factor after integration. So this is what you will get. As a result, after 3 steps, get the following chain. Now you clearly see that we are simply reconstructing our asymptotic series step by step. After 3 iterations, we recovered first 3 terms in our series. And the integral term is simply the integral representation of the remainder or error. Let's rewrite the result as follows. Obviously, we may go on and make n steps to recover the first n terms of the series in the form of the exact equation. Here is our partial sum of the asymptotic series. And let's write down the integral defining the error term. This way, we have just built rigorously the asymptotic series with simple integration by parts technique. The procedure, being free of approximations, also allowed us to obtain the integral representation for the error term. Our next goal is to estimate and minimize the error term. So I basically show you the full theory of asymptotic series on this particular example.